Good morning. This is screencast number 1 for lesson 3 of Unit 8. Okay, we're going over global weather patterns. How do the atmosphere and ocean affect global weather? Well, by the end of this lesson, you should be able to explain how circulation in the atmosphere and oceans affect global weather. Okay, your Texas Essential Knowledge and Skills down here. Identify the role of the oceans in the formation of weather systems, such as hurricanes. Okay, we're going to go to page 452 and start here. Weather. First of all, weather is a short-term state of the atmosphere at any given time or place. And weather includes many factors: temperature, humidity, precipitation, air pressure, wind speed, and direction, and visibility. All of those are part of weather. Hopefully you have some sort of basic familiarity with those since we've been taking data which includes most of those factors on a daily basis. All right, so we need to talk about how is solar energy related to weather. Well, first of all, we need to understand that the sun does not warm all of the Earth's surface evenly. Areas near the equator receive more incoming radiation from the sun, and over time at the equator or near the equator, incoming solar radiation is greater than the radiation that goes back into space. So the Earth receives solar radiation, and some of it is in turn lost, goes back out into space and is lost. But at the equator, we typically keep more solar radiation than we lose. So we get a surplus of solar radiation at the equator or in the tropics. Okay, surplus meaning extra. In contrast, the middle latitudes and the poles receive less incoming solar radiation than they lose. So middle latitudes to the poles, yes, they're receiving solar radiation, but they're not receiving as much incoming solar radiation, and they're actually losing more than they're receiving. So they're at those latitudes, there's a deficit, which means there's a shortage. So at the equator, we're getting more than we're losing. We have a surplus. And towards the poles, we are losing more than we're getting, which is a deficit. Okay? Well, so it's really important for you to understand, in order to understand global weather, it's really important to understand that we have to get the extra heat from the equator, and we have to do our best to redistribute it towards the poles. Okay, and I say we. That's what the Earth does naturally. Okay, energy as heat is transferred from the warm tropics towards the colder poles, and it's done in two ways. We move or we transfer heat energy through atmospheric circulation, and we transfer heat energy through oceanic circulation. Okay. All right. The map down here shows you, you've got sea surface temperatures here. So this is a map showing you surface temperatures of the ocean. Red is warmer, and purple to black is the coolest, and this is in degrees Celsius. So you see that you have very warm water in the tropics and much cooler water towards the poles. Okay, so we have to try to redistribute, take some of this excess heat and move it towards the poles. All right, page 453. What are convection currents? This is not the first time we've talked about convection currents, and we keep talking about them because they are very, very important. Okay. Energy as heat is transferred mainly by convection. Remember that convection is the movement of matter due to differences in density, which is caused by differences in temperature. Warmer fluid is a little bit less dense, and so it tends to rise. Cooler fluid is a little bit more dense, and it tends to sink. Okay? And when we have a cycling of warmer, less dense, and cooler, more dense, matter, then what we get is a convection current. In the ocean and the atmosphere, convection currents transfer energy as heat from the tropics towards the poles. So we're going to have large-scale convection currents that are acting both in the ocean and in the atmosphere that help us to take the excess heat at the equator and move it towards the poles. Okay. Now, here it says warm, moist air rises in the tropics. The air cools as it travels towards the poles, and cold, dry air sinks at the poles and travels back along the surface of the Earth towards the tropics. This cycling of air forms convection cells. Add the label warm or cold to the boxes in the diagram to show the air temperatures at the poles and the equator. Okay. The poles, we're having cold air. At the equator, we have warm air. Okay. And I'm not real sure where this one is supposed to be, so we're just going to leave that. Okay, now I need to warn you about this particular diagram. This is a nice, simple diagram of how we would have convection cells set up if the Earth was not rotating. Okay, we would have one big convection cell going from the equator towards the North Pole. We'd have one big convection cell going from the equator towards the South Pole. And winds would be able to go directly from the pole back to the equator. This is simplified because this does not take Earth's rotation into consideration. So you need to be careful on this one. Okay, because we know from previous lessons, lesson 1, that what we wind up having is something that's more complex that looks like this. And we have multiple convection cells. And the reason that we get that is because of the Earth's rotation. Okay? If the Earth was not rotating, like I said, we would have these single cells in the northern and southern hemisphere. Okay? So just keep that in mind. All right. Let's move down. All right. What factors create patterns of global weather? Well, we have both atmospheric patterns, or atmospheric factors, and we have oceanic factors. So global weather patterns are going to be influenced by what's going on in the atmosphere and what's going on in the ocean. Okay? So the weather where you live is affected by global weather patterns. Global weather patterns are widespread, covering thousands of square kilometers, and they often are driven by interactions between the atmosphere and the ocean. Okay? Down here, it talks about important atmospheric factors, such as wind systems that flow across the Earth, areas of generally high or low pressure, and seasonal changes in wind and pressure. Okay? And I went ahead and took the information from this paragraph and kind of listed it. Okay? So your atmospheric factors, global wind systems, high and low pressure areas, seasonal changes in wind and pressure. Down here, important oceanic factors that affect global weather include the movement of surface water and sea surface temperatures. So again, I summarized it down here. Your oceanic factors that are going to affect the patterns of global weather, your movement of surface water, and sea surface temperatures. Okay, now what I'm going to do before I go on to the next screencast is I'm kind of going to give you an idea of how the rest of the lesson is organized. Okay, so if you notice on page 454, we're now going to talk in more detail about those atmospheric factors that we just looked at. Okay, so now we're going to talk in detail about the atmospheric factors all the way to there. Then beginning on page 457, we're going to talk about the oceanic factors affecting global weather. Currents, movement of ocean water, and then finally the page 460 and 461 where it says Children of the Pacific, we're going to talk about El Nino and La Nina, because those are atmospheric factors, sorry, not atmospheric, oceanic factors that have to do with sea surface temperatures. Okay, so the first part of the oceanic factors has to do with currents, and then the second part has to do with actual factors due to sea surface temperatures. Okay, and that'll take us through the rest of the lesson.